My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 570. In this lecture, I will continue my discussion on SGD recap. Before understanding this lecture, I request all of you to go through my previous lecture, that is lecture number 569, in which we discussed about this particular slide. Just recall that slide. We discussed derivative of loss function with respect to w by using mini batch SGD and gradient descent. Yes, let me continue. We were saying that we want to compute dou L by dou W with the gradient descent, but this we are calculating mini batch SGD. Why? Because calculating this dou L by dou W with respect to mini batch SGD is easy. I can say this mini batch SGD is an approximation for gradient descent. Just I request all of you to go through my previous lecture. Here let me assume this is my W, this is my L of W. Let me say yes. Now suppose this is my W naught. Let me assume this one is W naught. My gradient is like this. This is my gradient, isn't it? And move this side. We are moving this side, isn't it? And keep moving towards this is W star. What is this? This is W star, optimal W, I can say. It is optimal W. That's minimum, isn't minima, isn't it? We keep moving towards W star in the case of gradient descent. Let's look at a couple of gradient. Just let me go to this Wikipedia page on gradient descent. Just see in what I typed in image search, gradient descent, Wikipedia. Just let me take this particular picture. Just see, this is the picture. Let me assume, let's assume W equal to W1 W2. Let's assume two-dimensional weight vector. We looked at this contour diagram in one of the previous lectures, in which we learned how to interpret contour diagrams, isn't it? In contour diagram, what does these lines means? These lines are, we discussed about these particular lines in contour diagram, isn't it? Loss at the points are same, isn't it? That's what the contour diagram says. That's what the contour diagram says. And the minimum loss is here. The minima that we want to, the loss is same. Just if you take any let me say this point, on all these particular curve, loss is same. Here you have W1, as well as on x-axis you have W1, on y-axis you have W2. Yes, this loss is same along this particular contour. Just we already interpreted about all these contours. Just I request all of you to recall this one, isn't it? What is the minima here? Just see, if you consider loss, along this at this point W1 W2, this loss is same. That's what we were discussing. What is this is the minima that we want to reach. This is the minima, isn't it? This is the minima that we want to reach. Let's assume your initial point is, where is your initial? This is the minima that we want to reach. This is initial point. I can say this is initial point. This is minimum loss, isn't it? Minimum loss is here. Therefore, this is the minima that we want to reach. Where is your initial point? This is your initial point, isn't it? How does gradient descent works? Gradient descent works very easily. This is a diagram from Wikipedia. This is my x naught. What is my x naught? X naught is initial point. It always point like this. It always try to move towards the best weight vector. It always try to move towards the minima, just like in this case, in the case of gradient descent in 2 dimensions also, what's happening? It always try to move the optimal one, isn't it? W star. Here also this is W star in this case, isn't it? Here This is W. It always try to move the best value of W, whether it is one dimension or whether it is two dimensions. When we use gradient descent, this gradient always points to optimal point, that is minima, isn't it? But what happens if you are using stochastic gradient? This is a nice diagram about just say this is about gradient descent. What about stochastic gradient? Just see SGD convergence. This is a nice diagram about a stochastic gradient. Just I Google search for SGD convergence. Just see. What about previous one? This is gradient descent, that you should understand. This is related to this particular diagram is related to GD, gradient descent, isn't it? Now if I go to if I Google search for SGD convergence, just see here, what am I writing here? This is SGD convergence. Just see, this is SGD convergence. I am searching for this. This is very nice diagram. Just what is this diagram here? Just see, this is the diagram we are getting. Yes, this is a very nice diagram. These are the, you know what is this diagram? These are the contours. This is the what is the minima here? Which one is the minima? This is the minima, isn't it? This is how you will converge to the solution. Just see how you are converging to the minima, how you are converging to the solution. W naught like this, like this, like this, like this, like this, like this, like this. Just see. Ultimately it is converging, isn't it? This is, you will converge to the solution in the case this is very nice diagram. These are the contour. This is the minima. This one is minima. This is how you will converge to the solution. You are converging to the minima, isn't it? Converging to the minima in the case of SGD. Previous slide is related to GD, that is gradient descent. This slide is related to stochastic gradient descent. Suppose this is my W naught. Where is my W naught? This is my W naught. This is my initial vector, I can say. Yes, my initial vector. If you look at this this case, what happens in the case of gradient descent? Just see, converge to the solution in the case of SGD. What happens in the case of gradient descent? Isn't it? It's going direct. The direction is it's not like SGD. Just see these directions, isn't it? But in the case of stochastic gradient, the directions are not like that, isn't it? Yes. If I apply gradient descent, you are getting different directions. But with SGD or mini batch SGD or one point SGD is an approximation to gradient descent. I will not perfectly always move in the direction. I will move. In the case of mini batch SDG or one point SGD, it is an approximation to gradient descent. That's what we discussed, isn't it? I will move in some direction. In the case of SGD, just see, in the case of SGD, I am moving in some direction. It's not a straight direction. I am moving in some direction like this. I am moving some direction like this, isn't it? I am moving in some direction, but eventually it reaches minima, isn't it? The mathematics behind SGD, both mini batch and one point, is if you run enough number of times or enough number of iterations, if you run lots of iterations of SGD, the W star is the minimum point that we get is same as W star with gradient descent is same as W star with stochastic gradient descent. That's what it says. If you run these algorithms enough number of times, what happens? Just see. If you run it enough number of times, your W star with SGD is approximately equal to W star with GD. Of course, GD is going to converge fast, isn't it? What happens? Gradient descent is going to converge fast in fewer steps. Gradient descent or GD converges in 3 or 4 steps. Stochastic gradient may take 10 to 15 steps. The cost of computing gradient descent, this is important, the cost of computing gradient descent is very, very large. That's why we are choosing stochastic gradient descent. So the mathematical proof, which is non-trivial to prove, shows that if you take lots of iterations, probably 5 iterations using GD converge to the minima in the case of SGD or stochastic gradient descent, you may require like 20 or 30 iteration, but eventually you will reach the same place. Now just see this one, this red lines, just in this particular slide I am again comparing stochastic gradient and gradient descent. Now the red lines that you see is the path that we take if you follow stochastic gradient descent. That is your W0, W1, W2, W3, so on, W7. Eventually, if you look at the dark blue line, just see this dark blue line is your gradient descent path, isn't it? Just if you observe this grade, just compare these two diagrams. So what's happening here, if you notice what's happening here, even though blue line has taken 4 steps, the red line have taken 8 steps, isn't it? But eventually converges to the same point. So you can think of SGD as eventually reaching maybe after many iteration to the same minima that gradient descent could reach. But SGD also has some problem. SGD is not pointing exactly in the direction of gradient, because look at in your mini batch SGD or in your single point SGD, the gradient we compute is approximation to gradient descent, is not exactly equal to the derivative of gradient descent. It's an approximation. So what's happening here is the estimates of derivatives. You can think of this whole thing as you are estimating your gradient. You are estimating your gradient or derivative. Gradient or derivative means same thing, isn't it? Estimating gradient or derivative means same thing using stochastic gradient. When you are estimating what happens, you get each of the updates completely depend on the derivatives. Depend on the derivatives. Derivative depends on what is update completely depends on your derivative, because the derivative defines your whole update literally. Given that fact, each of the updates are more noisy in mini batch SGD or single point SGD than in the case of gradient descent. GD, that is gradient descent, is straightforward from one point to other point to W star, isn't it? Your stochastic gradient, on the other hand, will keep moving this way, that way, eventually it reaches W star. So each of these updates are more noisy, isn't it? So here next learn a concept on how to denoise data, because in the case of noisy points, one of the major problem with SGD is it gives you noisy updates to the gradient. So we somehow come up with denoising the gradient that we get from SGD so as to converge faster. If you denoise them, your convergence will be faster. In my next lecture, we will try to understand how to denoise this. Just try to go through this lecture, and if you have any difficulty, please keep a comment. Thank you very much.